Hi everyone. Now we'll see important concepts, okay, for GATE and engineering service students, okay. So subject is structural analysis. So in last class I explained preparation strategy, okay. I explained important topics, okay. Now here we'll discuss few important questions, okay. So don't think these questions only will ask in examination, okay, it's not like that, okay. Just we are expecting few important questions, okay, right. The first question, right. Now just see the question. In a rigid jointed frame, the joints are considered. Okay, this is the question from first chapter, right? Introduction. Chat box open. Right. Yes, hi Suraj Chaudhary. Right. Now can anyone answer for this question? D. Chaudhary. No. Wrong. In first chapter, I given a difference between rigid joint and pin joint, right? Okay. If the members are connected with more than single bolt or welding, which joint? Rigid joint. Yes or no? Now here this column beam joint is a rigid joint, right? Okay. So joint B and C are rigid joints. Okay, right. Prince option B, no. Right. Anyway, just look here. This is before loading. Now, if we apply the load for this, okay, this is before loading. What is the included angle between the members for this diagram? It is 90 degrees, right? Included angle between the members, it is 90 degrees before loading. Now, if we apply the load, for example, we'll apply the load exactly at the center. For example, W, this is L by 2, this is also L by 2. Then how it will deflect? So slope at the fixed support is 0, right? Okay, then so it will deflect like this. Okay, so this is called deflected curve, also called elastic curve, right? Okay, right. Students, I given one point. At the rigid joint, rotation in all the members are same. Yes or no? At the rigid joint, rotation in all the members are same only. Okay, it means, look here, this is the joint B and this is the joint C, rigid joints. Okay, now rotation of beam at a joint B, clockwise or anti-clockwise? Clockwise. And rotation of column at a joint B, clockwise or anti-clockwise? This is also clockwise. Now these both are same direction or different direction? Both are same direction. Students, at the rigid joint, rotation of members are in same direction only. It means at joint B, if beam rotate in clockwise direction, column also rotate in clockwise direction only at the same joint. Okay, now if you see joint C, at a joint C, rotation of beam clockwise or anti-clockwise? Rotation of beam at joint C towards joint C. anti-clockwise. Then rotation of column toward the joint C also anti-clockwise. Both are same direction. Okay, so students, at the rigid joint, rotation of members are in same direction only, not in different direction. Okay, then here at the rigid joint, before loading, included angle between the members 90 degrees, right? I told rigid joint, at the rigid joint, rotation in all the members are same only. It means if beam rotate by an angle theta b, column also rotate by an angle theta b only. Okay, if the beam rotate by an angle theta c, then column also rotate by an angle theta c only. Okay, it means at the rigid joint, if the number of members are meeting 2, 3, 4, 5, whatever it is, at the rigid joint, rotation in all the members are same and same direction. Okay, now tell me students, what is the included angle between the members? What is the included angle between the members after loading? So this is the included angle. It is 90 degrees only. It is remain same at the rigid joint. Now tell me students, rigid joint will rotate or not? Yes, there is a rotation at joint B is theta B and there is a rotation at C is theta C. Yes, rigid joint will also rotate but not individual. Complete joint will rotate. Rigid joint will rotate as a whole. Okay, then only you will get the included angle between the members remains same. Now students, can anyone tell the answer now? I give an explanation. Okay, so rigid joint will rotate as a whole. Entire rigid joint will rotate. Okay, it means option A is correct. Clear? Right. So here option B is given not to rotate at all. It won't rotate. It will rotate, right? There is a theta B and there is a theta C. It will rotate. Right. Next question. So for this diagram, can you find the static indeterminacy? Can you find the static indeterminacy? What is the degree of static indeterminacy of the plane structure as shown in the figure below? Now this is a question from second chapter, right? Static indeterminacy. Okay, so this is called hybrid structure. Okay, right. First, at the fixed support, number of reactions are 3. Okay, it is not clear. Okay, number of reactions are 3. And at the hinged support, number of reactions are 2. And at the fixed support, number of reactions are 3. Right. So what is the formula to find the static indeterminacy? First we'll find the external indeterminacy. What is the formula to find the external indeterminacy? R minus S. Okay, here R is number of reactions, right? Okay, so how many reactions here total? 3, 6, 8. So number of reactions are 8. And for rigid jointed plane frame, equilibrium equations always 3 only, right? For rigid jointed plane frame. Okay, then what is the DSE value here? DSE value equals to 5. Okay, then what is the internal indeterminacy formula? DSI, it is 3C. What is C here? Number of closed boxes. Okay, so how many closed boxes here? Number of closed boxes how many? 1, 2. So number of closed boxes are 2 equals to 6. Okay, then next, force releases. Okay, now students tell me which hinge it is. This is the axial hinge, right? And this is shear hinge. Okay, For axial hinge, how many force releases? Can anyone tell? For axial hinge, how many force releases? Okay, so number of force releases are here 1, that is axial force. Okay, then here also 1, that is shear force. Okay, the number of force releases are 2. Okay, now what is the static indeterminacy formula? DSE plus DSI minus force releases. Okay, so DSE we got 5, DSI 6 and minus 2. Okay, then equals to 9. Then option D is correct. Yes or no? Right. Now we'll see the next question. Right. So this is the multi-selected question. Okay. Which of the following structures are internally unstable? Okay, internally unstable. Okay, the students, if you see first diagram, okay, if you see first diagram, this is a roller support, number of reactions are only 1, that is vertical. Okay, and this also roller support, number of reactions are 1, and here also roller support, number of reactions are 1. Students, tell me, these 3 reactions are parallel to each other, right? Yes, 3 reactions are parallel to each other. Then, due to horizontal force, rigid body translation takes place, right? Yes or no? If all the support reactions are parallel to each other, rigid body translation takes place. Okay, now this is externally unstable. Okay, this is externally unstable. Okay, students, external stability deals with support reactions and internal stability deals with stability within the structure, right? Okay, right. Now second diagram, is it stable or unstable? Second diagram. Okay, so these are roller support. Here one horizontal reaction, okay, and here vertical reaction, and here inclined reaction. Okay, now students, if you see line of action of this vertical reaction, okay, and line of action of this horizontal reaction, okay, and line of action of this inclined reaction, then all the support reactions are meeting at single point or not? Nothing but concurrent. If all the support reactions are concurrent, also a unstable structure. Okay, so if all the support reactions are parallel, rigid body translation takes place. If all the support reactions are concurrent, rigid body rotation takes place due to movement. It means here horizontal equilibrium equation is not balancing. Okay, then for second diagram, moment equilibrium equation is not balancing. Okay, so this is also unstable, but this is externally unstable. Okay, externally unstable. Next, third diagram. Students, this is simply supported beam with internal hinge, right? Simply supported beam is stable structure, but simply supported beam with internal hinge is unstable structure, right? Okay, now if we apply the load, okay, if we apply the load, so it will deflect like this, right? So it will deflect like this. So what is the variation of deflected profile here? linear. Okay, if the variation of deflected profile is linear, then it is called unstable, right? Yes or no? The variation of deflected profile is linear in mechanism. Okay, so here this is internally unstable. So this is internally unstable. Okay, right. Then option D. What is the perfect shape of the truss? Triangle, right? For internal stability of truss, did you remember I given three conditions? If m equals to 2j minus 3, perfect frame. If m greater than 2j minus 3, redundant frame. If m less than 2j minus 3, it is internally unstable. Okay, then students, here the perfect shape of the truss is triangle, right? Okay, then there is a triangle shape is missing or not here. Okay, there is a triangle shape is missing in this panel. So this is internally unstable. So this is internally unstable. So in the question, he is asking which of the following structures are internally unstable. Okay, what are the internally unstable? C and D. Okay, this is the multi-selected question. Okay, so C and D is the answer. Okay, right. Next question. Now this is the next question. This is also a multi-selected question. The frame shown below is or kinematically indeterminate by 3. Okay, asking which diagram has dk value equals to 3, that is after neglecting axial deformation. Can you find the dk for these 4 diagrams? What is the dk? Students, is it a sway frame or non-sway frame? This is. And students, I want to tell you one point here. Already explained, if I won't show any load on the structure, it is called general load. General load means over these structures, horizontal load is present, vertical load is present. Just think about unsymmetrical loading. Okay, remember, I repeat, if you won't show any load on the structure, it is called general load. General load means horizontal loads are present, vertical loads are present. Just treat these loads are unsymmetric loads. Okay, right. Now students, first tell me, is it a sway frame or non-sway frame? Is it sway or non-sway? Chaudhary, sir, D is the perfect stable. Okay, this is not perfectly stable. Chaudhary. If you use the formula, you will get m equals to 2j minus 3 only. Okay, if you use the formula, you will get m equals to 2j minus 3. Then most of students will think this is called perfect frame. Okay, I told formulas not always correct. Okay, formulas not always correct. I am not saying formulas are not correct. I am saying formulas are not always correct. Okay, so the perfect shape of the truss is triangle shape. How this formula we got m equals to 2j minus 3? Reason is, for example, if I remove one member here, then triangle is present. Okay, this is become internally unstable because of improper arrangement of members. Okay, improper arrangement of members, it is become unstable structure. Is it clear, Chaudhary? So if we provide this member here, then it will become stable, perfect frame. But this is unstable. Sir, if internal hinges present in the beam, which kind of force releases? Moment releases. Moment release. Internal hinge cannot resist movement, right? Which forces it cannot resist, those forces only we are releasing here. That is the force releases concept. Okay? Right. Right. Now here, so this is the non-sway frame. Okay? So at the beam level, will it free to move in horizontal direction? No. This supports will not allow to free to move in horizontal direction. Then this is non-sway frame. Okay? This is non-sway frame. The students, neglecting axial deformation, okay, find the decay, simply count the number of rotations, right? Okay, count the number of rotation. Fixed support, no rotation. Fixed support, no rotation. Fixed support, no rotation. Okay, at the rigid joint, there is a one rotation. At the rigid joint, if the number of members are meeting 2, 3, 1000, whatever it is, we have to consider only one rotation at the rigid joint, because at the rigid joint, rotation all the members are same only. Okay. Now here at the hinged support, there is a one rotation. Now how many degree of freedoms? 2 degree of freedom. These two are rotations only. Okay. Then second diagram, this is the rigid jointed plane frame. Okay. Fixed support 0, 0. Rigid joint 3, rigid joint 3. Now dk equals to 6 total. Okay. Then neglecting axial deformation, deduct the number of members. Deduct number of members. How many members are there here? Number of members are 3, right? Then equals to 3. Okay. So we need kinematic indeterminacy by 3. Then B is correct. Next, fixed support 0. And is it sway frame or non-sway frame? At the beam level, will it free to move in horizontal direction? No. So this is non-sway frame. Okay. Now at the hinged support, one rotation. And students, there is a internal hinge, right? At the internal hinge, how many rotations? Here rotation, here rotation. Okay. Then here 2. These are neglecting axial deformation, students. Okay. This is the one with axial deformation, here 4. With axial deformation is 4. Neglecting axial deformation is 2. And here only 1. Now your dk equals to 3. Neglecting axial deformation, then option C also correct. Okay, C also correct. Then here how many degree of freedoms? Neglecting axial deformation, here one rotation, here one rotation, here one rotation, here one rotation, and here one sway. Now what is the dk value here? Dk value equals to 5. Okay, so what is the answer? Here B and C are correct. Okay, B and C are correct. Right. Next question. Now this is a question from third chapter, that is analysis of determinate trusses. Okay. In analysis of determinate trusses, we have to find the force in truss members, right? I given shortcuts. Okay. And 2 methods are there, method of joint and method of section. Okay. Right. First we'll try with shortcut in examination. If shortcut is not possible, then next priority we have to use method of section. If method of section also not possible, then next we'll use method of joint. Okay. So the force in the member AC. Okay, asking to find the force in member AC. Now which member is AC? Now this is the member AC. Okay. Now students, this is the roller support, right? Now here there is a vertical reaction RA. Okay, vertical reaction RA. Now students, this reaction treat as a member. Okay, this reaction treat as a member. Okay, right. Now, it is a joint A, how many members are meeting? 4. I'm saying this reaction treat as a member only. The number of members are meeting at joint A is 4. And students, these two are collinear and these two are collinear. Nothing but pair of collinear, right? It means force in member AC equals to reaction RA value. Okay, so force in member AC equals to reaction RA. Both are same only. Now if you find the reaction RA sufficient. How to find the reaction RA? Taking moment about another support. Okay, now we'll take moment about taking moment about support B. Okay, so what are the sign conventions? Anti-clockwise negative, clockwise positive. Okay, right. Now target is support B, right? Right. Tell me, RA clockwise or anti-clockwise? This is clockwise, positive. RA into what the perpendicular distance up to support B? It is 4. Okay, force into perpendicular distance. Next, here this horizontal load 6 kilonewton, will it develop moment about B? No, because line of action of this load meeting at B only. Similarly, this 6 kilonewton also will not develop moment at B because line of action of this load meeting at B. Okay, but these two will develop the moment. Okay, now tell me students, this two clockwise or anti-clockwise? This two, it is clockwise. What the perpendicular distance? 3 meter, right? Okay, so here plus 2 into 3. And this two, this is clockwise or anti-clockwise? Towards support B, this is anti-clockwise. And what the perpendicular distance? 3. So minus 2 into 3 equals to 0. Okay, then here plus 6 minus 6, then what is the reaction RA? It is 0. Now here force in member AC equals to 0. Okay, right. Next question. Which of the following statements is or correct for the analysis of plane trusses? Okay, right. Here the number of equilibrium equations are 2 for method of joint. Yes, in method of joint, equilibrium equation of a joint is considered. Okay, then we'll use equilibrium equation of a joint. Then for pin jointed plane frame, number of equilibrium equations are 2. What are the 2? Sigma H equals to 0, sigma V equals to 0. Then option 1 is correct. Okay, so here in option C there is no 1. In option D also there is no 1. You can eliminate C and D. Okay, in examination better eliminate the options. Okay, option 1 is 100% correct. Okay, so in option C there is no 1 and in D also no 1. So eliminate C and D. Then here A and B. In A 1 is present, in B also 1 is present, then 3 and 4. Okay, then we'll check option 2. Okay, it is possible to find the more than 2 unknown forces at a joint by method of joint. Students, in method of joint, number of equilibrium equations are only 2. And using 2 equilibrium equations, we can find only 2 unknowns at a time, right? Not more than 2 unknowns at a time, but he given more than 2 unknowns. So 2 is wrong. Okay, so here 2 is wrong means C and D wrong only. Okay, then next 3, the number of possible equilibrium equations are 2 for method of section? No. Okay, so how many equilibrium equations in method of section? It is 3, right? It is not 2. What are the 3 here? Sigma h equals to 0, sigma v equals to 0, and sigma m equals to 0. Okay, so in method of joint, equilibrium equation of a joint is considered. In method of section, equilibrium equation of a structure is considered. Then for pin jointed plane frame, for structure, equilibrium equations are 3. Then option 3 is wrong. So it means B is wrong, then only A is correct. You want check? 4 you can check it. It is possible to find the more than 2 unknown forces at a joint by method of section. Yes, method of section, 3 equilibrium equations are there. We can find more than 2 unknowns. Okay, then 4 is correct. So only 1 and 4 are correct, then option A is correct. Yes, very good. Right. Next question. So statement 1, statement 2 questions. Okay, IES. Right. Statement 1. In trusses, bending moments and shear are small in comparison to the direct forces. Direct forces means axial forces, right? Okay, students, I given few assumptions. Truss members are subjected to only axial forces, because in truss members there is a shear force and bending moment also practically. Okay, but shear force and bending moments are negligible and we will neglect. Okay, and we are assuming truss members are subjected to only axial forces. Okay, so here statement 1, is it right or wrong? Yes. So in trusses, bending moments and shear forces are small in comparison to the axial forces and usually not considered in their design. Yes, statement 1 is correct. Okay, statement 2, if 4 members are meet at a point, okay, 4 members are meet at a point forming 2 pair of collinear members. Okay, students, this is the point, and 4 members are meeting and these are the pair of collinear. Okay, pair of collinear. Look here, these 2 are collinear. Okay, and these 2 are collinear. Now this is called pair of collinear. In case of pair of collinear, students, force in this member both are same magnitude, same nature. Same nature means, same magnitude means, for example, here in this member, if it is a 10 kilonewton right side, then force in this member is same magnitude but opposite direction 10 left side. This is right side 10, this is left side 10. Same nature means both are either compression or tension. Look at here, this arrow toward the joint compression, this arrow toward the joint compression. Okay, for example, force in this member if it is 0, force in this member also 0. Okay, so it means here, if 4 members are meet at a point forming 2 pair of collinear members, yes, 2 pair of collinear members, and there is a no load at this joint, there is a no external load at this joint. Okay, then the forces in collinear members have same magnitude and same nature. Yes, same magnitude and same nature. Same magnitude means here 10, same magnitude. Here 0, here also 0, same magnitude. Same nature means if it is compression, here also compression. If it is tension, here also tension. Okay, then statement 2 also correct. Okay, now tell me students, both statements are true. Statement 1 is true, statement 2 also true. Okay, now tell me, statement 2 is a correct explanation of statement 1. No, there is no relation between these two statements, right? So both statements are individually true. Okay, so here both statement 1 and statement 2 are individually true, and but statement 2 is the not correct explanation of statement 1. Then option B is correct. Okay, yes, very good, Yashwant. Right, next question. Okay, next question. This is the question from rolling loads and influence lines, ILD. Okay, what are you asking? 2 point loads of 4 kilonewton and 6 kilonewton spaced 6 meter apart crosses a girder 16 meter span. The 4 kilonewton load leading from left to right. The maximum bending moment under 4 kilonewton is. Students, in this question, section is not given, but he is asking to find the bending moment under 4 kilonewton. If the section is not given, it is called absolute maximum bending moment. If the section is given, we'll find the bending moment at the section. If the section, if it is not given, we'll find the bend. This is called absolute maximum bending moment. Okay. Now here, how many loads are given? 2 loads. Okay, moving from left to right, left to right. And which one is the leading load? 4 kilonewton loading is leading. Then another one is 6 kilonewton. And spacing between these two, 6 meter. Okay, right. Students, in the question, if you won't mention type of beam, always consider as a simply supported beam only. Okay, so what is the span of beam? 16 meter given. So this is 16 meter. Right. So first, can you find the center of gravity of loading system? Okay, consider, and this is the leading loading is given, right, in the question, leading load, and assume this is the reference load. Okay, what is the formula? 4 into, what is the distance between 4 and the leading load? Both are same, 0, plus 6 into 6 and divided by, okay, here 4 plus 6. Okay, can you one tell this answer? I think this you will get 3.6 meter. Yes, 1036 and 10, yes, 3.6 meter. Okay, so here, but he asking to find the bending moment under 4 kilonewton. Okay, then if it is 3.6, then what is this value? Okay, then this is 2.4 meter. Okay, this is 3.6. But remember students, he asking maximum bending moment under 4 kilonewton only. Okay, right. Now, section is not given. We have to mark the center of beam, right? This is the center of beam. This is 8 meter and this is 8 meter, center of beam. Okay, tell me here 4 kilonewton, is it left to the resultant force or right to the resultant force? 4 kilonewton, it is right to the resultant force. Then place the 4 kilonewton right to the center of beam, that is okay, at what distance? What the distance between resultant force and 4 kilonewton? 3.6, right? Always half of the distance, always half of the distance. So what is half of the distance here? 1.8 meter. Okay, then draw the ILD for bending moment under 4 kilonewton. Okay. Then students, this is the distance A and this is the distance B, and this ordinate value is AB by L, right? What is the distance A here, and we'll place the load here. Okay, so this is A equals to 9.8 meter. Yes or no? A is equals to 9.8 meter. And what is B here? 6.2 meter, right? Right. Now here 9.8 into 6.2 divided by 16. Okay, right. So what is the load here? This is the 6 kilo Newton. Okay, what is the distance between 6 and 4 meter? 6 meter, right? If it is 6 meter, then this is 4.2 meter. Okay, right. Now can you find this distance? This distance. So this is 3.8 meter. Okay. Now using similar triangle, can you find the ordinate here? This ordinate using similar triangle. A distance of 9.8 meter. What is the ordinate? 9.8 into 6.2 divided by 16. And we need a distance of 3.8. What is the ordinate? Okay, so here 9.8 get cancelled. Okay, then this is 3.8 into 6.2 divided by 16. Okay, students, if I do any calculation mistakes, just check it please. Okay, now absolute maximum bending moment. Just load into ordinate. Okay, so 6 into, what is the ordinate here? 3.8 into 6.2 divided by 16 plus 4 into, what is the ordinate here? 9.8 into 6.2 divided by 16. Okay, and solve this, you'll get the answer. I think this is, you'll get 24 kilonewton meter. Then option D is correct. Okay, right. Next question. So this is a question from energy principle chapter. Okay, a rigid jointed frame ABC shown in the figure given, and he asking to find the horizontal displacement of point B. Horizontal displacement of point B. So what is the formula to find the horizontal displacement? So horizontal deflection, that is integration of 0 to L capital Mx small mx by EI dx. Okay, first can you find the capital Mx value? And what are the sign conventions we have to use? Sagging, positive, and hogging is negative. Okay, right. First, member capital Mx, small mx, then integration of 0 to L capital Mx small mx by EI dx. Okay, so what are the members are there here? Member CB, member BA. Two members are there, right? Okay, right. First we'll find the capital Mx. just consider a section at a distance of x. Consider a section at a distance of x. First we'll find the capital Mx. Okay, now here to find the bending moment at this point, either look left to the section or right to the section. Left to the section or right to the section. Okay, so just look right to the section, no load, then no movement, then here it is 0. Okay, then remember BA, just force into perpendicular distance, right? That is 10 into x. This develops sagging or hogging? This develop hogging bending moment, right? Then minus 10 into x. And in the question he asked him to find the horizontal displacement of point B only. Okay, it means to find the small mx value, remove the external load, okay, 10 kilonewton, and in horizontal direction apply virtual unit load, right? It means in place of 10 kilonewton, will apply virtual unit load, right? It means just in place of 10, substitute 1. Okay, it means here minus 1 into x. Then what is the length of member BA? H, right? Then 0 to h. Okay, capital Mx minus 10 into x, and here minus x by EI dx. Okay, now students, horizontal deflection of B is, what is the integration of x here? Integration of x square is x cube by 3, right? Okay, then here 10 h cube by 3 EI. Okay, 10 into h cube by 3 EI. So 10 into h cube by 3, then option A is correct. Okay. Right. Next question. Right. Determine the vertical deflection of joint I. Vertical deflection of joint I in the truss shown in figure due to increasing temperature of 10 degrees Celsius in the bottom cord members. There is an increasing temperature only in this bottom cord members. It means there is no changing temperature in rest of members. Okay. Now students, what is the formula? Summation of k into delta, right? No need to find the k values in all the members, because here delta equals to L alpha T. In the question given, there is a changing temperature only in this bottom horizontal members, right? Then we have to find the k values only in this bottom horizontal members. Okay, but here length of these bottom horizontal members are same, 5, and is the temperature rise or fall? Temperature rise. For temperature rise, then delta is positive, right? Okay, then what is the alpha value given? Alpha value is given 12 into 10 to the power of minus 6, and what is the changing temperature is given? 10. Now this is the delta value only in bottom horizontal members. Okay, right. Now look at here. It means we have to find the k values only these 4 bottom members. In rest of members, t value is 0. If t is 0, then delta is 0. Then 0 into k values, 0 only. So this is the reason no need to find the k values in all the members. Okay. Now these are points are given here. So this is a vertical deflection at I formula. Okay. So here for temperature rise, delta is positive. Okay. Next, L alpha T, that is 5 into 12 into 10 to the power of minus 6 into 10. This is a value you will get, and this is an important note point. Okay. Since only bottom cord members are affected by the temperature change, then a downward vertical unit load is applied at a joint I, and because of symmetry, only left half of the truss need to be analyzed. Okay. Right. Look at here. We have to find the vertical deflection at joint I, right? Then apply virtual unit load only at a joint I in vertical direction. Okay. Now here vertical reaction is 1 by 2. Here vertical reaction is 1 by 2. And what is the horizontal reaction here? Horizontal reaction is 0. Okay. Now students, this is symmetry, right? Because of symmetry, then analyze either left part or right part, any one part, because force in this member same, and force in this member are same. Now students, here force in this member is 0, right? Because the horizontal reaction is 0, then don't consider 0 reaction. Number of members 1, 2, 3. These two are in same line, force in third member 0. These two are in same line, force in third member 0. Now students, we have to find the force only in this member or in this member. Okay, so how to find the force in this member? We'll use method of section, cut the structure like this, okay, and do analysis for left part of the structure. I given this note point. Do analysis for left part of the structure. Okay, now students, we have to find the force in this member. This is wanted member, right? And these two are unwanted members. Where these two unwanted members are meeting? At joint D. It means moment equilibrium equation about D is possible. Okay, so moment about D is possible. Okay, so here anti-clockwise negative, clockwise is positive. Okay, now taking moment about D, look left side. We are doing analysis only for left part of the structure, right? Now this is clockwise and this is anti-clockwise, right? Now if you see here, force, this is clockwise and anti-clockwise. Anti-clockwise. What the perpendicular distance? 6. Now here KHI into 6. And this reaction is clockwise, right? So 1 by 2 into what the perpendicular distance? 5. So 1 by 2 into 5. Then from this you will get the force in this member, that is 0.42. Okay. So here we got positive. Then assume direction is correct. We assume tension, right? Yes, it is tension. Then force in this member also, it is same, 0.42 tension. Then substitute in the formula. So here how many members are subjected to forces? 2 members, right? Just multiply with 2. Okay, multiply with 2. Why 2? Because only 2 members are subjected to forces, this member and this member. Okay, so he will get the value 0. We are asking in terms of mm, right? Okay, so 0.504 mm. Okay. Right. Next, statement 1, statement 2. Statement 1, energy principles are used extensively to determine the displacement in the structure. Yes. So in energy principle chapter, we'll find the displacement of structures only, right? In strength of material, you'll find the deflection of beams. But in structure analysis, you'll find the displacement of frames, rigid jointed frames and pin jointed frame. Okay. So statement 1 is correct. Now statement 2, Castiglione's first theorem is useful in analysis of statically indeterminate structure. Yes, what is the Castiglione's theorem 1? Partial derivative of total strain energy with respect to displacement gives force. This is the Castiglione's theorem 1. Okay, and while his second theorem is extensively used in computing displacement in the structure. Yes, what is the Castiglione's theorem 2? Partial derivative of total strain energy with respect to force gives displacement. Okay, so statement 2 correct. Now tell me students, is there a relation between statement 1 and statement 2? Statement 2 is the correct expression of statement 1? No. So both are individually true, then option B is correct. Okay, right. Right. Next question. Right. So the value of moment at C generated for the loading condition acting on the rigid frame shown in the figure below is. So he asking to find the moment at C. First students, here we'll use the moment distribution method. Okay, use the moment distribution method. First, I explained shortcut, right? What the condition for shortcut? Just check it. Stiffness for member BA, stiffness for member BC is the same or different? Stiffness for member BA, foreign disc fixed support. What is the stiffness? 4EI by L. What is the length here? 4 meter, right? Then this is EI. What the stiffness for member BC? Stiffness for member BC, foreign disc fixed support, 4EI by L. What is the length of member BC? 4 only, then EI. Now tell me student, stiffness values for member BA and BC both are same, and this is the non-sway frame, then you can use the shortcut. So what the shortcut here? So moment at B, here fixed end moment is here clockwise, okay. So here fixed end moment for member BA, and there is a no load, here fixed end moment is 0. Now tell me student, what is the fixed end moment for member BA? Subjected to UDL clockwise plus WL square by 2L, right? Subjected to UDL, okay. So what is the shortcut? WL square by 2L, okay, and plus 0 divided by 2. Then this is WL square by 24, okay. So what is the W given? 2. What is the span? 4 square divided by 24, okay. So I think this you will get 1.33 kilonewton meter. But he asking to find the moment at C, right? Moment at C is equals to, there is no external load, right? So half of the moment at B, okay. So what is half of the value? Then this is 0.67 kilonewton meter. This is the shortcut, right? Then option D is correct. Right. Right. Next question. This way can occur in the portal frames due to the following. Okay, sway can occur. Columns can be of unequal heights. Yes, if the height of the columns are different. Okay, this is L1, this is L2, this is the sway frame. If column heights are different, this is the sway frame, yes. And the moment of inertia of the columns are not equal, yes. If the moment of inertia of the columns are not equal, also it is called sway. For example, moment of inertia of left column is 2I and right column is I. So this is the sway frame. Okay, then 2 also correct. And a symmetrical frame is symmetrical. Yes, this is the symmetrical frame, okay, subjected to anti-symmetric loading. For example, this is the loading, this is a distance of 3 meter and this is a distance of 2 meter. Okay, so loading is unsymmetry, then this is also a sway frame. So 3 are correct. Okay, so 1, 2, 3, then option D is correct. Right. Next, all the members of the frame shown below have the same fragility EI. The rotation of joint B is. Student, this is a non-sway frame, right? This is the non-sway frame. So how to find the rotation at B? Use the joint equilibrium equation at B. Joint equilibrium equation at B. What is the joint equilibrium equation at B? What the members are meeting at B? BA, BC equals to 0. Now write the slow deflection equation for member BA. MBA equals to MFBA plus 2EI by L 2 times of theta B plus theta A, and delta is 0 because this is the non-sway frame. Delta equals to 0. Okay, right. What is the fixed end moment for member BA? No external load. fixed end moment for members BA is 0, and slope at A is 0 because it is fixed support. Okay, and what is the span here? Length is 4 meter, right? Then 2 2, then this is EI theta B. Similarly, write the slope deflection equation for member BC. This is MF BC plus 2EI by L 2 times of theta B plus theta C minus 3 delta by L, but delta equals to 0. Okay, and support C is fixed support, slope at C is 0. Okay, and what is the fixed end moment for member BC? This is anti-clockwise, right? Okay, so what is the formula? Fixed end moment for member BC minus point load, this is WL by 8, right? What is the W value? W is given 4 and the span is given 4 divided by 8. Yes or no? Then this is equals to minus 2. So this is minus 2 and span is 4. Then this is EI theta B. Now substitute equation 1, equation 2 here. Okay, so substitute here. What is MBA? EI theta B and plus then minus 2 plus EI theta B equals to 0. Then from this equation, can you find the theta B value? This is 1 by EI, right? 1 by EI radian. Then option A is correct. Right. Just 5 minutes, students. Next, statement 1. In slope deflection method, the joints are considered rigid. Yes. Okay. All the intermediate joints. Okay, all the intermediate supports are rigid joints only in continuous beam. Okay, if it is a rigid jointed frame, so these two are rigid joints only, right? Okay, then in slope deflection method, the joints are considered rigid, which means that loads are applied on a structure, no change in value of angle between the members at the joint. Yes, students, I told at the rigid joint, if I apply load something, then it will deflect like this. Okay, it means this is the rotation at B, this is also rotation at B. Now at the rigid joint, rotation both the members are same in same direction, right? Okay, then here also this is a rigid joint, this is a rigid joint. Okay, so statement 1 is correct. In slope deflection method, the joints are considered rigid, which means that as the loads are applied on the structure, no change in value of angle between the members. So angle between the members remains same only. Before loading it is 180 degrees, after loading also 180 degrees. And before loading it is 90 degrees, after loading also 90 degrees. Okay. Then statement 2. In slope deflection method, the unknowns are the rotations of the joints. Yes, in slope deflection method, what the unknowns? Displacements are treated as unknowns. Okay. So both the statements are correct. But there is no statement 2 is the correct expression of statement 1? No, both individually true, then option B is correct. Yashwant, sir, can you explain column shear equation? Now it is not possible, Yashwant. I'm sorry. Right. Next question. This is the question from plastic theory chapter. A propped cantilever ABCD fixed at A and propped at B and with overhangs BD shown in figure carries a concentrated load W, ultimate load at the center of the span AB, okay, and a load alpha WU at the free end D, okay, and the value of alpha, what is the alpha value you asking? Okay, right. First, can you find the DS for this diagram? Find the ds. Here number of reactions 2. Flat member purely vertical load. Neglect the horizontal reaction. Neglect horizontal equilibrium equation. Okay. Then here it is 1. So total number of reactions are 3 and equilibrium equations 2 equals to 1. How many number of possible plastic hinges? 1, 2, 3. Where 3? At A, B and C. How many plastic hinges are required to form the mechanism? ds plus 1 equals to 2. Then can you find the number of possible independent mechanisms? So here 3 minus 1 equals to 2. What are the 2 here? Beam mechanism in span AB, beam mechanism in span BD. So beam mechanism in span AB and BD. Okay. So students, can you find the collapse load or plastic moment for beam mechanism in span AB? First, last question students. Beam mechanism in span AB. So this is a diagram given. This is L by 2. So this is the ultimate load and given alpha ultimate load. To get the mechanism only in span AB, where to provide the plastic hinges? Then mechanism will form like this, right? Okay. So this is delta and this is delta 1. Okay. So what is external work done? Anyway, this is theta, theta, and this is theta, and this is also theta. So mark the direction of plastic movement opposite to the rotation where there is a plastic hinges, right? Okay. So what is external work done? Load and displacement both are same direction, collapse load into delta, and the load is downward but displacement is upward different direction. Okay. So alpha ultimate load into delta 1. So here what is delta here? L by 2 into theta. What is delta 1? What is the span given here? L by 2 only, right? So this is delta 1 also L by 2 into theta. Okay. So collapse load L by 2 into theta minus alpha collapse load L by 2 into theta. Okay. This is external work done. Next, internal work done. Just MP into theta plus MP into theta plus MP into theta. Then this is 3 MP theta. Okay. Just from this equation, can you find the collapse load? From this, or find the plastic moment. Just equate external work done equals to internal work done. So what is external work done? Collapse load L by 2 theta equals minus alpha collapse load L by 2 theta and internal work done 3 MP theta. So theta, theta, theta get cancelled. Then from this equation, find the plastic moment. Okay, find the plastic moment. Okay, just you do this calculation. Next, beam mechanism in span BD. Beam mechanism in span BD. So where to provide the plastic hinges to get the mechanism only in span BD? Provide plastic hinge here. It will deflect like this. This is the rotation and this is the plastic movement and this is the delta. What is delta here? L by 2 into theta. So what is external work done here? Alpha ultimate load into delta. What is delta? L by 2 theta. And what is internal work done? Just MP into theta, right? MP into theta. Now equate external work done equals to internal work done. So alpha ultimate load L by 2 theta and MP into theta. So theta get cancelled. Okay, so from this equation you will get the alpha ultimate load L by 2 theta. This is equation 2 for example. And this is the equation number 1. Okay, just equate equation 1 and equation 2. Equate equation 1 and equation 2, then you will get the alpha value. Okay, so I think you will get the alpha value, some value you will get. So alpha value you will get, students, 0.25. Okay, alpha value will get 0.25. Okay. So these are the few questions I given here. So already taken 20 minutes extra. Okay, so I'll stop it here. Okay, students. So students, just concentrate on important topics. And don't ask me now what the important topics. Day before yesterday, I explained important topics. Okay, just concentrate on those important topics. And don't solve only these questions, please. There are the few models, this type of questions, model, we are expecting in GATE and ESE. Okay, right. Chalo. Okay, shall I end the session, students? Yes, thank you, Nitin. Okay, so students, all the best for your examination and for your multiple colorful future. Okay, thank you.